Hi, everyone again. Thank you, Zoom. It's my pleasure to introduce our speaker today. This is the second of our fall semester's Center for Climatic Research Climate, People, and Environment Program seminar. And for those who don't know me, I'm Ankur Desai. I'm the CPEP professor and nominal organizer of this thing. So I have the pleasure of getting to introduce all our wonderful speakers. So hopefully you're staying warm wherever you are in this otherwise chilly, rainy fall day here in Madison. And we're going to hear a little bit more about how all these things come to be in terms of weather dynamics to land and atmosphere from Dave Kristovich. Dr. Kristovich is the head of the Climate and Atmospheric Sciences section of the Illinois State Water Survey of the Prairie Research Institute. And then he's also affiliated as an adjunct professor at the University of Illinois in atmospheric science. Dave has his degrees, his bachelor's from Rutgers University in meteorology and his master's and PhD from the University of Chicago. He's been involved in a number of field projects, broadly involved in areas of lake and land atmosphere interactions, and he's also the editor-in-chief of the Journal of Applied Meteorology and Climatology. I got a little bit of taste of the creativity of Dave's work when several years ago I took a class of students from AOS down to the Savant Field campaign in Illinois, where we had to spend our hours in the middle of the night while people were blowing smoke and shooting lasers into the sky, trying to figure out what's going on with the nighttime stable boundary layer on these farm fields. And it was really cool to see how all these measurements can kind of come together to tell us a story about these very hard to otherwise visualize and measure phenomena. And today I think we'll be hearing about one that is actually one that we can easily observe, but maybe one that we don't know actually a lot about. And so the title of today's talk is In Situ Observations of Clouds and Snow in Lake Effect Snowstorms, which I know is a favorite of a lot of people on this call. So I'm going to hand it off to you. If you got questions during the talk, feel free to add them to chat and I will save them for the end of the talk. And we'll have some time for Q&A toward the end. And then, yes, feel free to drink your coffee and eat and stuff. This is a lunchtime seminar, so go for it.
Okay, thank you very much. And I won't be monitoring chat, so if someone needs to interrupt me, I suppose either speak up or Encore, feel free to jump in to literally be back at the University of Wisconsin a lot of good collaborations over the years, a lot of good friends that I've developed on your campus, and I'll mention a few of those along the way. This is also very exciting for me because it's the first time that I've been able to give a formal seminar wearing sweatpants and clown shoes in honor of my mother-in-law. So, so it's a first for me in many ways. But what I'm going to be focusing on today is lake effect snowstorms, and I'm going to start off by talking a little bit about the basics of lake effect snow, what we know about lake effect storms, and what we don't know as much about, and then spend most of the time talking about a project that we just started a couple of months ago, and that we'll be carrying on hopefully for the next couple of years. So let's see. Okay, just wanted to briefly mention a couple of things that we're doing outside of the lake effect realm. Encore mentioned the Savant project. That was a field project in central Illinois, where we were looking at nocturnal drainage flow down gullies, very shallow gullies in central Illinois. So that was one of our projects where we were literally outstanding in the field. And in this case, the cornfield and soybeans. We have a number of instruments that we take observations with. One is a halo Doppler LiDAR, which is in the center picture down at the bottom. In this case, we were measuring airflow associated with boundary layer rolls. And a lot of the discussion today will be on the OWLS project. I have a photograph taken from the University of Wyoming King Air as we flew over a lake effect snow plume, cloud plume over that developed over one of the Finger Lakes. So it was really a dramatic, very local snowstorm that developed in that area. Types of work that we do is related to, we do some work in pollen capture. We have an aerosol LiDAR as well as the Doppler LiDAR. Aerosol particle counters, tethered balloons, radiosondes. We are very expanding our interests in a lot of different ways, taking observations that aren't typical for us. Exciting in terms of getting to try new things and getting out in the field. So, so I'll be talking a little bit about some of those. Okay, so fundamentally, lake effect snowstorms tend to develop during the what in boundary layer is the unstable season. And that's a season where climatologically, at least in this case, the water temperature, which is the blue line, is warmer than the air temperature. And this tends to occur anywhere from July or August on occasion throughout the winter and into March. And during this time period, when the lakes are warmer than the overlying air, it's like the cold air flowing over a hot plate or a boiling pot of water, where you have intense heat and moisture fluxes from the surface that manifests itself in modification of the atmosphere, the lower atmosphere, and ultimately snow that we're quite familiar with here. So the result of those fluxes can be a little schematic drawing here. It can be in the development of an unstable convective boundary layer. Unstable is redundant, but a convective boundary layer, which as the air in this diagram flows from the left to the right, you get cold air flows over the relatively warm water. Waves aren't usually that big, and you get a development of convection that rapidly rises in the first half, in the upwind half of the lake, and then tends to rise more slowly over the downwind half of the lake. Within that boundary layer, you tend to get cloud development. A little bit of the moisture comes back down to the ground in the form of snow. So that's fundamentally what lake effect is about. Of course, in the Great Lakes, we have more than one lake. I lived in Chicago, so I thought there was only Lake Michigan, but really there are extra other lakes out there. And this is a schematic of what happens when you have two lakes, where you have the colder air moving over the second lake, and you get a secondary development of a convective boundary layer and sometimes very intense snow, more intense even over the eastern lake, or over to the lake that's further downwind. So that's the general setup of lake effect. But there's a lot of these processes that we really don't know and have not documented very well. In fall and winter, you'll often see satellite images that look like this, where cold air is flowing southward across Lake Superior in the upper left here. And after some distance out over the lake, shallow clouds begin to develop, and downwind from that, you tend to get snow. And these systems can last for days on end. This particular snowstorm lasted, I think, 36 hours, depending on how you count the beginning and end of that particular storm. We also have lake effect that is more or less visible on all of the other lakes. We have these widespread bands over Lake Huron and Lake Michigan, some more single types of bands over the eastern Great Lakes, and one over Lake Erie is well hidden in this example. even in February, Lake Erie had some openings in the ice cover. Michael Notaro and a number of other people, Mark Cooley, we're working with them on a NASA project looking at lake effect storms and the ability of the NASA NU-WRF model to improve its ability to simulate these types of systems and other types of boundary layer phenomena. So we're glad to be helping out with that a little bit. So you can look at lake effect from a lot of different standpoints. And of course, the question that very frequently comes up is lake climate impacts or changing climate impacts on the Great Lakes. There's a recent study by Don Webbles and a number of other authors who looked at how climate change might be expected to change the physical characteristics of the lakes, such as lake depth, how high the lakes might be in the future, regional climate change. We all know the Great Lakes have their own effects on the regional climate. Climate change is expected to affect the Great Lakes area a little bit in a modified way than it will in the rest of central North America. And of course, these changes will affect hydrology, ecology, and society, which is a big driver for why we do this kind of work. And we are involved in a number of projects related to several of these components. So the Great Lakes are very important, and when you're looking over long time periods, they raise a number of challenges to our ability to predict and understand what is likely to happen. On more of a meteorological, short time scale, lake effect snowstorms can be thought of from a number of different standpoints, and I show some of them here. The upper left is boundary layer growth, the development of a convective boundary layer over a lake as the air moves from, in this case, Wisconsin to over Lake Michigan. These are lines of constant potential temperature, and you can see how these well-mixed boundary layer, the depth of that increases rather rapidly across the lakes in this example. You can look at lake effect from a climate standpoint. Been some really good work on this, especially in in several recent decades, as well as within the last year or two. But a student of mine, Luke Bard, found that the increase in lake effect snow, which has been reported over much of the Great Lakes, over Lake Michigan, we saw the beginnings of a decrease in snowfall. These are 5-year averages. Starting in the late 70s, early 80s, that type of pattern has now been reported in New York State. So this reversal is a bit of a, right now looks like it might be more pronounced in the southern Great Lakes areas. Forecasting, of course, that plays a very big role in why we care about lake effect. And you can look at these storms from the standpoint of turbulence and boundary layer processes. This is just an illustration of the characteristics, the buoyancy of updraft and downdraft cores. And by cores, we were looking through aircraft data and picking out time periods of tens to hundreds of meters where the aircraft observed a consistent updraft or downdraft. And the red are the updrafts, the blue are the downdrafts, and you can see there's positive buoyancy with the updrafts up to about halfway up into the boundary layer on this case. On the downdrafts tend to be cooler than the atmosphere. That's cooler than the average temperature, and that's partly related to snow evaporation. And at the top of the boundary layer, all heck breaks loose with a huge amount of variability. And I'll be talking about that a little bit more and work we're currently doing with that. So there are a lot of different standpoints. One of the more popular standpoints is from looking at the mesoscale convective structures. These are several very common or widespread convective structures over Lake Superior, where you have these multiple cloud bands. We have a shoreline band or a long axis parallel band. In this case, we had two north-south oriented deeper cloud bands, which were producing heavy snow in northwestern Indiana. On the right side, we have a mesoscale vortex that we occasionally see. This particular vortex formed along a trough that was crossing Lake Michigan. Local heating and shear associated with horizontal shear associated with that trough generated a very clear mesoscale vortex that we were able to do some pseudo dual Doppler analyses with. So that's by Neil Laird. There are other features that I don't show here. There are gravity waves, which Greg Tripoli looked quite a bit at after one of our earlier collaborations, and other more local types of systems that you could pick out for any of the Great Lakes. But regardless, the ultimate part that we're most worried about and think a lot about in terms of forecasting is the amount of snow and the types of weather that you can get during an intense lake effect snowstorm. This is a snowfall accumulation map over a 3-day time period in December of 2016, where more than a meter of snow was measured in parts of the Tug Hill Plateau east of Lake Ontario. I'm in Illinois, we never see anything like that. It's remarkable snowfall amounts that you can get. And here are some of the other types of weather that were observed. 3 inches of snow per hour at Buffalo and Waterton. Lightning was reported, an 84-mile-an-hour gust at Oswego Harbor. Had some roofs blown off. Highways closed. Snowplows were sliding off of the roads. And unfortunately, there was one death related to snow removal activities. So these systems can have a great deal of impact on society and on areas close to the Great Lakes, and we tend to focus on snow as one of the primary impact-driven efforts. Few of my favorite pictures of lake effect snowstorms. On the lower left, we see snow removal activities, which I think is a little bit futile when you have snow piles of snow that are outside. I always feel like that's going to collapse back on to the road. In the middle, I had a 5th grader asked me if these were rabbits. No, these are full-grown deer with their heads sticking out of the snow. And this was in the UP of Michigan, and in 2010, I believe. And of course, the deep types of snow that we see affecting buildings and other structures and roadways on the eastern, in some of the eastern Great Lakes as well. So, so snow is easy to focus on as an important factor. But the interesting thing about lake effect snow is we actually know very little about the snow processes themselves. And there are a number of reasons for that. We're getting close to the year 2000. Because of all the problems with parameterizations, what parameterizations are ideal for microphysics, for snow and cloud growth, aerosol development, as well as convective parameterizations. There are a lot of unknowns about which are ideal, and just a couple of decades ago, Peter Sasunas was mentioning the weaknesses with measuring quantitative precipitation or estimating quantitative precipitation using mesoscale models. More recently, Peggy Limon talked about one of the key uncertainties in current modeling systems and large eddy simulations, where precipitation is one of the key questions to how precipitation and clouds affect boundary layers. There are still major questions and aspects that we don't fully understand. Reeves and Dawson conducted a wonderful project looking at varying microphysical as well as boundary layer turbulence schemes in mesoscale models. They found that the schemes themselves tended to give different regimes, different types of lake effect. One resulted in narrow shields of precipitation with a lot of graupel, which is very dense snow particles. Since they fall rather rapidly, more rapidly than dendrites or other lighter types of snow, the snow wouldn't tend to reach further inland. Change the parameterizations around a little bit, and you get a whole different regime where you have light snow that extends farther inland. And of course, the atmosphere doesn't care about parameterizations. It just comes up with one of these solutions for any particular. And over again, and I can list another 5 or 6 papers that say that the biggest problem with improving our models is the lack of observations of snow development over the Great Lakes. And there are a lot of reasons for that. The biggest one is in most lake effect situations, all the exciting action occurs out over a lake. And over the years, I've had very little luck getting graduate students who want to go out in canoes on lakes in the middle of winter, launching balloons and taking measurements. So, so it's very hard to take over lake observations from an in situ standpoint. You could do a little bit better with remote sensing radar and satellite types of analyses. But these are some of the recent, and I'll call them medium to large size field projects that have occurred since the 70s and 80s. University of Chicago project was focused on Lake Michigan. There's Lake Ontario project, which ended up focusing on ice storms associated with lake effect. And moving on down this list to more recently, the Ontario Winter Lake Effect Systems project, which was occurring in 2013 and 2014. There are dozens of other smaller types of field projects that are designed to take specific observations, and some great work has been associated with them as well. But those are some of the larger systems. So for the rest of the presentation, I'm going to be focusing largely on owls, since it was the most recent lake effect storm. Our particular interest here at the University of Illinois was on the snow growth, snow initiation in lake effect storms, as well as how the lakes interact with each other to provide snow on over the eastern Great Lakes. How does Lake Michigan, for example, affect lake effect snow on Lake Ontario? Those types of questions. Owls was a moderately large field project, a number of people involved through various regions in the US. And we had a number of platforms from which we were taking observations, and I'm only showing a couple of examples. There's quite a bit more. Of course, we had surface observations of snow. Just here we have a nice photograph of one snowflake. We had balloon soundings and vertically pointing profilers and flux towers. These in the middle, but a nice site south of Lake Ontario. On the top right, some of you will recognize this as the Doppler on wheels, which you often see in the media, especially in their work looking at tornadoes. We had 3 Doppler on wheels systems that were deployed in owls and gave us exceptional data. and a few other things. The lower right is the University of Alabama MIPS system. It's a boundary layer and precipitation system set of instrumentation. The platform I used most often is the University of Wisconsin King Air. So focusing on the King Air, these are the types of flight patterns that we tended to do. This on the left is the height of the aircraft at different times. And you'll see the aircraft flew from Penn Airport and did a sawtooth type of pattern up near the, over the southern shore of Lake Ontario, and flew back and forth at different heights to, so that we can measure how the edges of the lakes affect the boundary layer processes. And so that's an example of the types of projects that we do. A lot of our work on snow developed over, as I had mentioned, over the western lakes, such as Lake Michigan. This is a cross-section of a convective boundary layer lake effect storm that occurred back in 1983. The lines are lines of constant potential temperature, and as I mentioned before, you can see the boundary layer growing in depth as you move from west to east. And cloud deck, which in the top panel, these are percentages of the aircraft time that were in clouds, liquid clouds. And started off when the clouds first developed, they essentially filled the boundary layer. These are not your typical clouds that have flat bottoms where it's very distinct. These were very ragged bottomed clouds that often with clouds extending down to the surface. And you'll see, and we've seen small water spouts. I hate to call them that. They weren't quite that strong, but water spouts, different types of microscale circulations that were going on. And interestingly enough, even though more and more moisture is being added to the atmosphere as you cross the lake, more if anyone has questions. On the bottom panel, we see snowfall, where snowfall occurred in this lake effect boundary layer, and by the time we got halfway over the lake, the boundary layer was entirely full. Those types of atmospheric processes were able to give us at least some outlines of the types of heat and moisture budgets that are part of the lake effect snow process. I won't go into details on this one, except to point out that two things. In lake effect storms, you have two sources of heating. One is the surface heating, which causes the buoyant updrafts and buoyant downdrafts that extend up through the boundary layer from the lake up to the top of the boundary layer. But those buoyant updrafts and downdrafts indirectly cause intense mixing at the top of the boundary layer, which tends to drag the warmer air in terms of potential temperature down into the boundary layer. So as the boundary layer, as a lake effect storm develops across the lake, you get heating from both above and below. The other issue I wanted to point out is we see this rather frequently, although it's hard to quantify. If you take all of the moisture that comes up from the lake surface and enters the air, how much of that comes back down to the surface in terms of snow? And when you're thinking about meters of snow, it's very easy to consider this as, you know, oh, much of that vapor must come down. But it's usually much smaller than that. In this particular case that they studied, only 13% of the upward flux of moisture came back down to the lake surface in the form of snow. And it's thought that it's usually less than half. Most of the vapor is going in to saturating the air, and that air is subsequently pushed downstream in the prevailing flow. We're able to do some work on the profiles of fluxes of water vapor, of liquid cloud droplets, and ice. And you get a clean, but a bit of a noise, you get a distinct pattern here, but it's fairly noisy due to the difficulty in taking these measurements. But in the lower boundary layer, we saw moisture fluxes that were quite close to the bulk estimates. And about halfway up into the boundary layer, the vapor fluxes rapidly decreased as the liquid, that's the development of clouds in your updrafts, and those clouds are carried vertically up to the top of the boundary layer. Some of this liquid, if you look at this quantitatively, there's a lot less liquid fluxes in terms of magnitude than vapor fluxes, and part of the reason for that is entrainment of dry air, but the other part of it is that some of that vapor and some of those clouds develop into snow, which falls down to the lake surface, even though it can often be a small percentage. So there's a lot you can learn when trying to understand the microphysical processes and how they interact with the dynamics of a boundary layer. But as you can see here, these are only a few isolated lake effect storms that occurred over Lake Michigan in relatively simple types of environments. As much as all of that looks very intriguing and it was good, solid results that could be tested numerically and theoretically, but when you get into the details, it becomes a lot messier. These are results of a study from a student of mine a few years ago, where she was documenting the size distributions of each of the cloud droplets. And to give you an orientation, there's an axis. All the axes for all of these plots are the same, but the vertical axis is concentration, increasing by 6 orders of magnitude. The x-axis is size of the cloud droplets, and you see this typical large numbers of small droplets and a few larger droplets that are mixed in. The slope of these particular lines gives you an idea of how rapidly cloud droplets develop, or how quickly they change from small droplets and grow into larger ones. So these are the cloud, kind of a quick outline of what the shapes of these distributions look like. And you can see as you move, the first clouds tended to form about 1/3 of the way across the lake. And as you move from west to east, you tended to get a few more larger droplets and a bit of and still large numbers of small droplets. So there's a little bit of cloud growth, but that is offset by snow. And these are the snow particle size distributions. These thick lines are again just what these distributions look like. There are 2 lines, though, 2 measurements. The light blue, or the thin blue line, and the red line. Those are 2 2D measuring systems that were operated at the same time. One is better at seeing large particles, one is better at seeing small particles, which is why they don't agree completely. But there are a couple of interesting features here. One is we have a lot of small droplets that you could see right near the upwind shore, with very few large snow particles. Get out over the middle of the lake, you can see there's an increase in concentration of all the sizes. If you compare these to these, the line has moved upward, meaning that the concentration is increased. But the slopes are about the same. There aren't many big particles. In this case, once we got to the middle of the lake, suddenly these distributions flattened out, which we interpret as the beginning of the aggregation process. And we do have some snow particle images that support this conclusion, that at some point over the lake, snowflakes become large enough that they start falling at differential speeds, the larger snowflakes falling faster, and they start running into the smaller snowflakes and aggregate and stick together. And that's where you get the large particles, large snowflakes, and a bit of a decrease in the small snowflakes as they've, in the concentration of them, as they start getting picked up by these large snowflakes. And that continues on across the lake. So there are some interesting puzzles here. What are the environmental conditions that determine when you start moving from all these small snowflakes to the ability to aggregate large snowflakes? Because we know from other types of microphysical studies that the initiation of aggregation is a big player in determining how much snow makes it down to the surface from any kind of snow generating system. So that's an interesting question that we need to explore. The other question is illustrated here. I mentioned that near the upwind shore, we saw no clouds, but we saw a fair number of snowflakes, which raises the question, how do you develop snowflakes without clouds being present? And we puzzled quite a bit about that over time. We think we understand it, but we're not 100% sure yet. These snowflakes could be snow that was sitting on the ground in Wisconsin, being picked up by the wind and blown up into the atmosphere. That's a good possibility, and that would be. But there were no reports of blowing snow on that particular day. Winds weren't that strong. They could be transient clouds that developed and then fall apart. They could be diamond dust, which are snow particles under very cold conditions that develop directly on aerosols, essentially just growing by vapor deposition to aerosol particles. It wasn't quite cold enough for that, though. So we think that the most likely scenario is we would get these small clouds that would develop at the top of the boundary layer. They would mix with the dry air above the boundary layer. Clouds would disappear, but the snowflakes would be left behind. They evaporate much more slowly, and so you could get some concentrations of snow particles that stick around for a while after the cloud has disappeared. Is that common? We're not entirely sure, but this kind of summarizes the types of observations that that Barthold found. There's another type of natural cloud seeding. When we conducted our study over Lake Michigan, we only had one good solid case of higher level clouds that were dropping snow down into the lake effect boundary layer. The lake effect boundary layer, you can see by these yellows and orange colored patches of heavier snow. They have a rather distinct cutoff point at about 1 kilometer depth. These clouds up above that are the seeding clouds, higher level clouds that were dropping snow down into the boundary layer. And what that seeding did was it tended to increase the concentration of all snow particle sizes, but especially the big particles. There were a lot more large particles observed when there was seeding occurring at the location of the aircraft, as compared to locations where there was no obvious seeding from above, where we tend to have smaller numbers of particles, as well as a lack of large ones. So seeding, in terms of estimated snowfall rates, dropping snow from a higher level cloud increased the snowfall rate by an order of magnitude, which is really dramatic if you're worried about shoveling your car out from under a pile of snow. So such seeding can occur, can be very, very important. The question is, how are things different over Lake Michigan, which I just showed, and over Lake Ontario, which is where the OWLS project took place? This is an example where we have a profile here of snowflake 2DC, snowflake concentrations in number per liter. Patches of clouds that the aircraft moved through These thicker lines here are just locations where the aircraft spun, where the aircraft did a circle before continuing upward. So it's just better horizontal measurements at these two locations. They don't really say anything about the atmosphere though, except that they were seeing snowflakes at those heights. These thick horizontal lines show the boundary layer top, the convective boundary layer top, which you can estimate from profiles of potential temperature, where you can see this capping inversion right up at about 900 meters above the lake, and a decrease in turbulent dissipation. Turbulence decreases, in this case, rather dramatically at about that same height. So that was how we were estimating the boundary layer depth. And we can see there's a lot of snow above the boundary layer, above the classic lake effect boundary layer. This is another example where we had 6 estimates of the boundary layer top. These differences are probably real. They're different locations over and around the lake. But you see a lot of snow up above the boundary layer top for all of these heights. And as compared to a 2-month project over Lake Michigan, where we only had 1 seeding case, where we had seeding from above, over Lake Ontario during during the AL's 2-month deployment, all but 2 cases had snow. So almost every case, we were able to detect some level of amount of snow above the boundary layer top. So it's a very different physics of what we observed over the eastern lakes as compared to over the western lakes. Now, I mentioned that when you have seeding, it can affect the snowfall rates. That's kind of expected with any kind of seeding, and in this case, natural cloud seeding. But we also have evidence that it affects the dynamics of the boundary layer itself. These are top panels of radar image taken by the Wyoming King Air, the Wyoming cloud radar, which was flown on the King Air as it flew over the boundary layer top on this day. And you can see these columns of snow, which are associated with the patches, the heavier patches of snow that you would observe if you were flying within the boundary layer. We have the Wyoming cloud LiDAR on the bottom image, and the LiDAR isn't able to penetrate clouds very well. So when we're in a cloud, you can only see the top of the cloud, the top edge of the cloud, kind of a thin layer around the edge of the cloud. And we can see quite a few clouds here and places where the LiDAR can see down into the boundary layer by some depth. You can see these yellows and oranges extending downward. Those are areas where there really weren't many cloud droplets, and the LiDAR was able to see further into the snow that was filling the boundary layer below it. But with this, you get a nice, clear map of what the top of the boundary layer looks like. And our earlier studies suggest that entrainment and boundary layer growth is enhanced when there's seeding going on. So latent heat release associated with snow formation can drive some of the dynamics of the storm itself, of the lake effect storm itself. And that's so there's an interesting dynamics, microphysics interaction. So there are a lot of things that we think we understand, but much more that we don't understand about lake effect microphysical processes, despite the fact that it's so important to our ability to simulate and predict lake effect storms. We also have not only with the microphysics, but with the turbulent characteristics, what turbulence parameterization should you use, for example. I said I pointed out earlier that there's a lot of questions about that. A postdoc, Sudhir, is conducting a study with us right now where he is looking at all of the aircraft soundings, which are the X's. And by aircraft soundings, I mean places where the aircraft rose or sank by over 800 meters, sometimes in the boundary layer, sometimes above the boundary layer. But it gives you a profile of what the atmosphere looked like over the 800 meters that the aircraft was flying. We also had 290 radiosondes launched, balloon launches of sounding systems. And you can see those around the edges, these diamond shapes. And those are well, diamond shapes as well as all these other shapes. We had 6 universities launching balloons around the lake. And those give us another measure. So combined over the course of the project, we have almost 400 soundings of within this lake effect system that gives a unique opportunity to understand and document how the boundary layer evolves across the lake, how the boundary layer changes from day to day, as well as the temporal changes over the entire lake effect system. So this is a very unique set of data that we collected during studying right now on with our group. So I'm just going to say a couple of things to wrap up here. We have a great deal of observations taken during the OWLS field project. If you're looking for some of our initial results from the project, the American Meteorological Society has a special collection on the OWLS project related papers. And I invite you to look for those papers in the AMS journals. We want to understand cloud and snow evolution a lot better than we do. We want to take more in situ observations, look at the environmental and mesoscale controls on the cloud and snow formation over the lakes, develop data sets that could be used to develop parameterizations, but also test parameterizations that others are using. And we're very interested in looking at what are the influences of natural cloud seeding, which we think are much more common over the eastern Great Lakes than the western Great Lakes. And so that's a big focus of what we'll be doing over the next couple of years. Okay, and we have a lot of people to thank. I'm not going to go through them all, but the National Science Foundation has funded both our initial grants as well as the current grant, continuing grant that I have now, as well as a number of other people that have helped with our lake effect efforts. So I think I will stop there. Are there any questions?
Cool. Thank you very much.
Thank you. I could hear the clapping.
Yes, right. Virtual applause. People can feel free to put up their favorite emoji. If you have questions, either you can try to use the raise hand feature and I'll look for them, or you can send them through the chat. And in fact, there is one right now, which I'll read to you. It says, climate models from the American Union of Concerned Scientists indicate by 2050 onwards, Wisconsin and cities like Milwaukee will see increased snowfalls in winter by 2050. Does lake effect snow play a major role, and how good are prediction methods to mitigate the effects on affected populations?
And that's an excellent question. And the results are currently mixed. There have been several specific studies for looking at how lake effect snow, not only how it has changed in snowfall over the last 4 or 5 decades, but also how it may be expected to change in future scenarios. And some of the studies have shown distinct increases in snowfall expected as the lakes warm and as opportunities for lake effect may increase. You might have an increase in lake ice. Other studies show a switch of lake effect snow into lake effect rain types of situations, which Kunkel and some other people have found with scenarios. It is really a good question. If putting together all of the studies I'm aware of, there's an inclination that lake effect may be increasing over the early half of this current century. We might have more lake effect rain later in the century, but there's still a lot of variability from one project to the next. And I'm not aware of anyone who has really done a lot of work combining synoptic scale cyclone generated snow to lake effect snow. I haven't really kept up on that literature as much, but I'd be very interested to see what they're finding.
Cool, thank you. So I've got another question in here from Ian Beckley. Says, I'd be interested to hear why cloud deck lifts over the leeward portion of the lake. And another commenter also interested in the same question.
Okay. Yeah, there are actually a couple of features of that. That was also one of the driving factors for wanting to conduct this study over Lake Ontario. In a lake effect situation, the lakes tend to be relatively smooth compared to the land around them. We don't have many trees and buildings in the middle of the lake. So, you know, those trees and buildings slow down the air once the air moves from lake to water. And that slowing down of the air gives you a bit of a convective boost. You have a convergence area that gives you a burst of snow near the downwind shore of any lake or most lakes. That has, we've seen situations where the clouds and the clouds have been increased by the order of 10 or 20% just by that small change in surface friction. And snowfall also increasing locally close to the downwind shore. Over lake or near Lake Ontario, to the east of Lake Ontario, we have the Tug Hill Plateau, which is a very slow slope, especially for those who used to live in who live in mountainous areas. It's a very gradual slope, but the clouds and snow can be lifted over the hills and producing dramatic amount of snow. We had several cases with over 3 meters of snow during individual snowstorms during the ELS project. And the cloud deck can be forced upward by the mountains or by the plateau. You could also have farther downwind from the lakes an uplift by mountainous regions which take the moist air and move it up. But it's not that, it's not as obvious or as simple as that may sound. Depending on the Froude number, there are situations where the air is simply too stable for the air to get lifted over the mountains. So in those situations, you get snow around the edges of the mountain as the air is being forced to the side. And that gives you a very different pattern when there's strong capping above the strong capping and maybe lighter winds near and above the boundary layer depth. So you can get lifting as the question suggested, but you could also get simply a redistribution horizontally of where the snow falls.
Interesting, thanks. Norm, I assume is Norm Wood, asks, is there an understanding of what the vertical profile of latent heat release looks like in lake effect snow clouds? I'm curious how different this might be from a typical convective cloud and how it influences LES cloud development.
Oh, wow, that's a wonderful question. I've shown you the example of at least observational studies of the vertical fluxes of heat and moisture. Very few studies out there using observations to estimate what that profile looks like. There are several differences that we see compared to a typical convective cloud, a vertical flux structure, buoyancy structure, for example. In these winter situations, there's a lot less moisture in the air. So when you get into the cloud base, you don't get as much of a increase in latent heat release as you would during the summer when there's much more vapor available for to re-strengthen and push the updrafts vertically in summertime cumulus types of convection. That's one of the big differences. The other difference has to do with the snow development. You in the cases that we've studied, we don't tend to have a small, I won't say small, we don't seem to have a local area of heavy snow with nothing around the outside, like you might get with an isolated convective system, for example. We tend to have snow everywhere, more intense in places than others, but the snow is easily carried around by just turbulent scale eddies. And that we see both at the top of the boundary layer when you're mixing in the dry air from above, as well as around the sides and around the edges of the system. So, so I would imagine that there are really distinct differences, but we really are hampered by a lack of extensive studies on that, although there have been some great numerical modeling studies that have compared such profiles. But the short answer is I don't really know exactly what they're going to look like, but you can guess what they would look like, and I'd like to conduct those studies.
Cool. Question from Ketzel Levins here. It says, what do you think needs to be done in order to understand why upwind shores have snowflakes observed but no clouds? And what has been observed on other Great Lakes?
Okay, I didn't hear the first part of the question. I'm sorry.
Sorry, that might have been my problem with there's orchestra class going on in the other room, virtual school world we live in. What do you think, what more do you think needs to be done in order to understand why upwind shores have snowflakes observed but no clouds?
Yeah, and that's a good question. This the case that I showed actually was an unexpected finding that we tended to see snow over within about 10 to 30% of the area had snowflakes in it. We weren't really expecting that when she conducted this study. So it was a bit of just a lucky choice of the case that we studied. But there are a few other studies that have pointed out some intriguing possibilities. Bram in the 1980s, early 1990s, pointed out that they would often see, over Lake Michigan, they would often see patches of snow within the boundary layer where there's no liquid cloud, but the snow isn't uniformly mixed. It's a local patch of snow, and they've run into those once in a while with the aircraft. That suggests that there was some local generating system that dropped snow and didn't have a chance to mix it throughout that region. So that's some intriguing findings that even over the western lakes, you might get upwind snow fairly often. In the eastern lakes, or the usual lakes that are downwind of other lakes, you can get snow that's dragged from Lake Erie to Lake Ontario, for example, and we saw that type of thing in a paper we just published. You could also have snow that's dropped from down into the lake. In fact, it's much more complex over the eastern parts of the lake, but we've seen that it's worth studying because it can make such a big difference to the lake effect system. Now, what do we need to do about that is an excellent question. And to me, one of the most useful things that I think we could do, in addition to some great simulations that should be done on looking at the impacts of snow developed, is to have a consistent upwind shore observation of not only surface snow, but snowfall within the lower atmosphere, within the boundary layer, upwind on the west side of Lake Michigan, for example, which isn't too far from you guys. That's a study that I really would love to see someone do, so we can get an idea of how often this occurs, you know, we'd be able to help out with some remote sensing type of instrumentation as well, if anyone's interested. But I really would like to see a lot more surface and especially above surface observations of precipitation particles.
Okay, I think with that, we should quit since we're at time. Thank you again for making the effort. I know we had originally scheduled you in last March, and that was the week when we just switched from in-person to virtual, so I'm glad we were able to reschedule and get you back. For folks following the seminar series, our next speaker will be Patricia Cleary, who's a professor at UW-Eau Claire who studies atmospheric chemistry and ozone, and she'll be presenting on November 9th at this same time. So hope to see you all there. And with
Great.
that, I'll thank our speaker again, Dave Kristovich, and hope
Right.
the rest of you have a great day.
Thank you very much.
Mhm.